Last time we discussed the interference pattern of two openings in the screen, which establish the wave character of light. Today I'm going to expand that to n, capital N, and we will make n thousands of openings in a screen. And when it comes to optical light, we call those gratings. So suppose here, each one of those dots is a small opening in a screen. Could be a small hole, or it could be a slit perpendicular to the blackboard. And imagine that plane waves are coming in. And so each one of those openings are going to be Huygens sources, and they're going to radiate spherical waves. And the question now that we want to answer is, if we look in a direction theta away from the normal to that screen, what is then the light intensity that you will see as a result of the interference of all these Huygens sources? Suppose that the separation between two adjacent Huygens sources is d. In other words, here is one and here is the other. So this is a blow-up of what you see here. Here you see hundreds, maybe thousands. Here I have only two. And if that separation is d, then I can calculate the phase difference between those two. If this is theta, this is no different from what we did last time for the double slits, then the path difference from this spherical wave to a point far away at an angle theta and this spherical wave, that path difference is this. And this is d sine theta. And so we will introduce, just like we did before, a phase angle delta, which is the phase between the spherical wave from this point and that point, from two neighboring points, and here there are thousands. So this is only between the two neighboring sources. And so first we want to know how many times can we fit a wavelength on this path. And for each time that we can fit a wavelength on there, we have a phase difference of 2 pi. So this delta is the phase difference. And we had the same equation last time for double slit interference. There's no difference. And if this delta is a multiple times 2 pi, then you will have constructive interference. My goal today is way more ambitious. I want to know what the light intensity is for any angle theta. It's going to be an extremely complicated function. I first want to revisit some of your high school geometry. If you have a triangle, and this side is A, and this side is also A, the length of the triangle, the length of the sides, and if you want to know what this one is, and if this angle is delta, then this side here is 2A times the cosine of 1/2 delta. You can revisit that in your high school geometry, but I need that today. And now I'm going to do the superposition, vectorially superposition of capital N E vectors that come from these various sources. And the neighboring ones are off by delta. That's the phase angle between them. I will raise this later, but I want to work above my head so that you can see what I do. I start with a circle. You will see shortly why I do that. The radius of the circle is unimportant. You will see that that will cancel. So this radius, arbitrarily chosen, is r. So this length here is also r. Call this point C, this point O, and this point P. And I'm going to add 3 vectors, which are all offset relative to each other over an angle delta, but I will make the calculation as if they were capital N. Capital N could be 1,000,000. There's no limit. But I'm going to make the drawing only for 3. This is one vector, and let's say it has a length A, but it's really the electric vector that is going to be add it vectorially to the other electric vectors. And so here is the other, the second one, and here is the third one. And so the angle between the second and the third one, this angle here is delta. And this angle here is also delta. That's the delta between the neighboring sources, which we just derived. It follows from the geometry of a circle that this angle here is delta, this angle here is delta, and this angle here is also delta. So that means if I have capital N of these vectors, that this angle here is then n times delta. And that means that the angle here, this angle, is then pi minus n times delta. I will draw one more line right to the middle of this vector. I think of this as length A, but it is the electric vector. You can also think of it as E0. And I draw a line straight to there. So this angle is 90 degrees. And so that means that I know that this angle now is 1/2 delta. And this is all the geometry that I need to calculate the incredibly complicated light intensity as a function of theta. My goal is to find the magnitude of the vector OP, because that's the result in this case of these three vectors, but I will make my calculation as if there were n. First, look at this triangle here, which has a 1/2 delta angle here. This is 90 degrees, and so this part here is 1/2 A. I just give it the length A. So that means that 1/2 A divided by R is exactly the sine of delta over 2. That's exact. It's not an approximation. It's not a small angle approximation. This is exactly the sine of that angle. In other words, my radius R is 1/2 A divided by the sine of delta over 2. So I'm really interested in OP. And now I'm going to use this knowledge. I have a triangle. I know two sides, and I know this angle. Then I can calculate this one. I know two sides. This is R, and this is R. I want to know the third side, and I know this angle, which is pi minus n delta, and therefore this length here is 2R times the cosine of half that angle, pi minus n delta divided by 2. But pi over 2 is 90 degrees, and 90 degrees minus the angle is the sine of the angle. So I can also write for this 2R times the sine of n delta over 2. Now I take this R here, and I pop that in here to eliminate my R. And so now I get that the length of that vector OP, which is really my goal, that is the vectorial sum of n E vectors, the adjacent ones off by phase angle delta, that is going to be 2 times R, so that gives me an A upstairs. And then I get the sine of n delta divided by 2, divided by the sine of delta divided by 2. And this is really the key of what is following. This is now the length, the magnitude of the E vector, if you think of this A as being E0. That's the magnitude of the electric field. So the light intensity, the pointing vector, obviously goes by the square. And so now comes the very famous equation that I, as a function of delta, is I0 times the sine of n delta divided by 2 divided by the sine of delta divided by 2, and this whole thing squared. And you could call this the grating equation. You will see that this is a very complicated function. We will beat it to death together. This is an exact derivation. This is no approximation. Delta can be anything from 0 to 10 million pi. There is no approximation made here. 10 pi, 20 pi, 30 pi, anything for delta is allowed. It's not an approximation. Now, the intensity, always think in terms of watts per square meter. And the meaning of I0 is that if there were only one opening in the screen instead of n, then this is the intensity that you would see I0. Now, if the upstairs here is 0, you would think that the intensity is 0. That is not always the case. Because if the upstairs is 0 and the downstairs is also 0, you get 0 divided by 0, and now you need L'Hopital to calculate what that ratio is. And that ratio then becomes the maximum value possible. So I write that here. So the maximum value possible, if you use L'Hopital, you will find that that ratio is n squared. And so this becomes n squared times I0. So that's the case when you get 0 divided by 0 in that equation. Before I will show you how dramatic this function is, I want to remind you that for n equals 2, which is what we covered last time, you can use this equation. This holds for any capital N. It holds for any value for delta. So if you substitute in this equation that you have there, n equals 2, and you do a little bit of massaging of the algebra, I will let you do that, you will find, so this is for the double slit interference, you will find that I is 4I0 times the cosine squared of delta over 2. And for those of you who have a good memory, remember that I derived this in class when you only have two vectors that you add, that the light intensity goes with the cosine square of delta over 2. Now you also have this here, so you also know that at the maxima, with two slits, you see 4 times more light than if there were only one opening. And you can do this, of course, on your own by substituting in this equation n equals 2. So the first thing that I want to do now is to make a drawing, a plot of that function, and I will do that for n equals 4. And then we will discuss all the consequences also for cases that n is much larger than 4. So I'm going to plot this for n equals 4. So we only have 4 openings now. And I always plot only sine theta. The reason why I like to plot always things in terms of sine theta, theta is a real geometrical angle. Here is this screen with the openings, and theta is an actual angle in the lecture hall. So theta is something that I can immediately relate to. This is 10 degrees, this is 20 degrees, this is 30 degrees. Delta is a phase angle, right? That's not a real angle in space. And so I always like to plot the intensity in terms of sine theta, but you can also do it if you want in terms of delta. All right, if sine theta is 0, then you get 0 divided by 0, and you're going to get a maximum. If sine theta is lambda divided by d, you're going to get a maximum. If sine theta is lambda divided by d, you see that delta is 2 pi. That means you get a maximum. So you get a maximum here. If sine theta is 2 lambda divided by d, you get a maximum. And of course, on the other side, minus lambda over d, you also get a maximum. And according to the equation, if you really believe that equation verbatim, then all these peaks would have the same maximum, which would be 16I0, because this is the n squared. And I will show you, but first I will plot it, that if there are 4 slits, that in between the prime maxima, there are n-1 locations whereby you have completely destructive interference. There's 0 light. n-1 in this case is 3. You will see shortly why it is n-1. So there are 3 locations here whereby there is 0 light. I put them in here, and then I will draw the curve. So that's the 0, and so I'm going to make an attempt now to draw the light intensity. So these are these prime maxima when 0 divided by 0 is n squared. Here's another one where 0 divided by 0 becomes n squared. And here's another one whereby 0 divided by 0 becomes n squared. If you wanted to know what the delta is here, well, the delta here is 0, of course. And the delta here is 2 pi. And the delta here is 4 pi. I first want to show you, or at least draw your attention to the fact that there is a wavelength-dependent lambda. And what that means is that if you take 650 nanometers, which is red, the red would have a maximum here, the red would have a maximum here, the red would have a maximum here, and the red would have a maximum there. But if now you have 400 nanometers, which is violet light, it would have a maximum at different locations. Here at 0, it would always have the same location, its maximum, but the wavelength is shorter for blue, for violet, so here would be the maximum for violet, here would be the maximum for violet, and roughly here would be the maximum for violet, and roughly here. The reason why the red and the blue there almost coincide, I mentioned that also last time for the double slit interference, is that 2 times 650 is roughly 3 times 400. So they live a life of their own. Let's now address the issue of the n-1 zeros. I first want to calculate what the location is here where you have your first 0. Complete 0. Well, you would have your first 0 when the upstairs is 0, but the downstairs is not 0. Because if they're both 0, you are at what we call a prime maximum. So what is the first time that this one becomes 0 when the downstairs is not 0? That is when this is pi. When it is 0, they're both 0. But when that is pi, then of course I would have my first 0. So let's do that here. So I call that my first 0. That is the case when n delta divided by 2 is pi. And so that means when delta is 2 pi divided by n. So now I go to this equation, and I put in here for delta 2 pi divided by n. And what you see then, that sine theta becomes lambda divided by sine theta is now lambda divided by nd. In other words, this point here, in terms of sine theta, which of course is the same as angle theta in radians because these angles are small. So this is an angular dimensional plot. So this here is lambda divided by nd. And then, of course, the second one will be twice lambda divided by nd, and the third one will be 3 times lambda divided by nd. You will again have completely destructive interference. You may be interested in what the magnitude is, what the light intensity, I should say, is of this little mini-maxima. Well, that is very easy to calculate. If we know that the sine of theta here is lambda divided by nd, and we know that here it is twice that much, then all I have to ask that equation, what is your light intensity when the sine of theta, so now we go to that minimax, the first minimax right here. So I ask the equation, what is your intensity when the sine theta is now 1.5 times lambda divided by nd? Then I'm right in between these two zeros. Now whether I'm exactly on that maximum, I don't know. I'm really not interested, but I'm surely I'm close. So, when sine theta is 1.5 lambda divided by nd, then delta is going to be 3 pi divided by n. That's easy because you take this equation, 1.5 lambda over nd. So you put in sine theta, 1.5 lambda divided by nd. The 1.5 times 2 becomes 3 pi. You get an n downstairs, so you get that delta is 3 pi divided by n. And now you revisit this equation, and you just put in there n equals 4. You know what capital N is. You know now what delta is, so you calculate the upstairs, you calculate the downstairs, and you will find now that I is approximately 1.17 I0. That's low compared to 16. This is only some 7%, 6.8%. So this height here is only some 7% of that height, so it's very low. So you have seen now the bizarre consequences that if you get 0 divided by 0, you get these maxima at 16 I0. Then you get n minus 1 points whereby you get complete zeros here, but even these mini maxima don't mean very much. They are very low in light intensity. And even if you go to an n of 1,000, and today we will even go beyond that with our experiments, and we'll have capital N, we go up to 2,000. If you make capital N 1,000, you can redo all this, and you will see that this mini maxima is roughly 4.5% of this maximum. That maximum now becomes 1,000,000 times I0. If you have 1,000 of these openings, they will add up at the maxima. You get 1,000,000 times the intensity that one alone would do. The reason is obviously you get 1,000 times the E vector, and they're all in phase with each other, and the Poynting vector is the square of the amplitude of the E vector. You get the million. All these maxima have the same width, and if this is lambda divided by nd, then this here on this side, in terms of angular distance, is of course the same. There's complete symmetry. And so the width here, if I take the width roughly, without being very precise, the width of each one of those peaks must be roughly lambda divided by nd. So I take half this distance, angular distance. All these things are angles in radians, because sine theta is very much smaller than theta. Now, you can see that the larger n is, the more of these openings you have, the narrower these lines are going to be, if I think of these as being a line, and that means your ability to distinguish two neighboring frequencies from each other, two different lambdas, increases, and that's what we call spectral resolution. So the larger n is, the better spectral resolution you have, your ability to separate two neighboring frequencies then increases. There is a very easy way that I can convince you, without any math, little math, why the width of these peaks, the width of these maxima, must be proportional to 1 over n. And that's purely an energy conservation argument. And follow me closely. If I have n of these openings in the screen, they will let n times more light through than one opening. That's straightforward. You can tell that to your kid brother. If you have n openings in the screen, you get n times more light through than if you had one opening. That's non-negotiable, right? But if each maximum is n squared times higher, the only way that you can conserve energy is if you make the maximum n times smaller. Then you know that n times more light went through. So the argument once more, you have n openings that give you n times more energy than one opening. But if each maximum gives you a light intensity which goes with n squared, the only way that you can conserve energy if you make the maxima n times narrower. And so that's a very easy way to see that the width here must go down with increasing n. Very powerful argument. Now I will make you see in another way, if we have 4 of these openings in the screen, why there are only 3 minima. And all these methods that I'm using, in a way, are complementary. It's all the same thing, but I just want you to see it in different ways. It helps me enormously to look at it in different ways. So we have n equals 4. And I start with delta equals 0. So there is no phase difference between adjacent sources. So this is the case that this is the E vector of source number 1, this is the E vector of source number 2, number 3, and number 4. All 4 E vectors line up in the same direction, otherwise delta could not be 0. Aha! Therefore I get 16 times the light, because I square 4E and I get 16. So this is your factor of 16. And you get a maximum. Now we go to delta equals pi over 2, 90 degrees. I don't have to look at that equation. I don't need that one. I know what 90 degrees is. I went to high school. I'm educated. This is one vector. This is 90 degrees. That's the second vector. This is 90 degrees. That's the third vector. This is the fourth vector, 90 degrees. What do I end up with? 0. So if all 4 relative to neighbors 90-degree phase angle, then clearly you have 0 here. Now I go delta equals pi. I know what pi is. 1, 2, 3, 4. What do I end up with? I add 4 vectors, 180 degrees, flip, 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 flip. What is the net result? 0. So it's dark. Here, this one is this one. And the second one is this one. Now I'm going to do this one for you. Delta equals 3/2 pi. 3/2 is 270 degrees. Well, this is 1, this is 270 degrees, this is 270 degrees, and that is 270 degrees. What is the net result? 0. So that's this one. Now I'm going to do 2 pi. When I do 2 pi, I'm back here. I get another maximum, and that's this one. And so you can see, purely by playing vectors, very simple, on a high school level, you can see that there will be n-1 minima, exact minima, between the prime maxima. So the first thing that I want you to see is when I take the grating that you have, and I use my laser pointer, the first thing I want you to see, incredible impact of using many, many lines. My laser beam has about a diameter of about 3 millimeters. So here is this laser beam, and this I estimated to be roughly 3 millimeters. Your grating, believe it or not, is a super grating. That grating has 13,400 lines per inch. Imagine how anyone can put grooves in your plastic. 13,400 per inch. That means that the separation D between 2 grooves is about 1.9 times 10 to the minus 6 meters. That is only 2 microns. How anyone can do that beats me, but it can be done. So I can calculate now how many of those lines I have here in the 3 millimeters. And I end up with n is about 1,600. So when I shine my laser beam through my grating, I use effectively 1,600 of those lines. And I can calculate now what the angles are where on the screen there, on the wall, the maxima will fall, those maxima. And by the way, there will be 1,599 of these zeros in between. And these minima are so small that you won't even see them. You will only see the maxima. So let's calculate at what angles we would then see the first. By the way, these things have names. We call this 0 order. And we call this first order. And we call, it's this one, yeah. This is first order. And we call this second order. And this is also called first order, but it is on the other side, of course. So we call these orders of the spectra. So you can now calculate that the sine of theta of n is n times lambda divided by d. And so when n is 0, that you zero's order, you get, of course, a maximum. So the zero's order is at theta equals 0. Now your first order is when the sine of theta 1 is lambda divided by d, and I can take my lambda, which in my case of my laser, I'll have to tell you, my lambda is 532 nanometers. It's green. And so I can calculate what theta 1 is, and I find 16.3 degrees. And then I can go to the second order, theta 2, for that color. It's different for different colors. And I find 34 degrees. And I can go to the third order, and I find theta 3 is then 57 degrees. And there is no fourth order. That would make the sign of theta larger than 1. So there are only 0 order, and then there are first, second, and third order. The grating that you have, I always carry that with me. No matter where I go, it's easy to put in your calendar. And so I will show you now by simply shining through this grating. I'll show you there on the wall. The 0 order would fall right smack in the middle, so to speak. First order, 16 degrees away. So if you know my distance to the wall, you can calculate how far that is. It's probably 1.5 meters. And so you will see these maxima. You will see them extremely narrow, high value for n. And, well, it speaks for itself. I have to rotate my gratings to make sure that the grooves are in this direction. If the grooves are in this direction, the spreading is out in this direction. So here you see. So the one that you see right now on the right side of the screen there is my 0 order. Now you can't tell that it is 0 order because I have only one color. And then you see, I will move it a little, you see the first order now on the right side of the screen. And that angle should be very accurately about what I calculated, the 16 degrees. And then you see on the blackboard here, you saw it right here, you see the second order. And then you see here the third order, if you have good eyes, and the fourth order doesn't exist. And imagine that between those maxima, if I really use 1600 lines, there would be 1599 points with exact zeros, and then all these silly mini maxima that you don't even see. So that is the power of a grating when you use many lines. If I use 1600 lines, I use 800 times more lines than when I have double slit interference. So the double slit interference pattern will be extremely different from this. That is why those locations are so narrow. Because if it were double slit interference, you would get the cosine square function, and so you would see the maxima would be 800 times broader than this. That's the power of using 1600 lines. Now I want you to get your gratings out, and I want you to look simply at a desktop lamp. And the reason why I want you to do that is that I want you to be disappointed because you may not see what you erroneously expected, that the 0 order is incredibly narrow. It is not. It's big. It's the lamp itself. Of course, if your light source in angular size is way larger than this angular size, you cannot expect to see the light source get smaller. In other words, clearly the limiting factor of seeing 0 order very narrow is only if the light source itself is small enough in size. And so when you look at this light now, you will see all colors at 0 order. That's one thing that's important. You just see the lamp. That's your 0 order maximum. That's the red, the blue, the green, the yellow, the violet. That's all of it. And then you will see on either side blue appear. First the blue, that has the lowest, shortest wavelength. I don't think there's much violet in this lamp. And then you will see the blue, the red. Make sure that you line it up so that the grooves are vertical, so that you get the spread in the horizontal plane. And then you see the green and you see the red, and it really looks like you have a spectrum, a continuous spectrum. Even at second order, it still looks like a reasonable spectrum. It starts in blue and it goes to red. But when you go to the third one, you already see that the blue and the red are going to interfere with each other there. So then they really don't look anymore clearly like separate spectra. So I want you to appreciate the fact that if your light source is huge, that each little location of the light source gives you a line which is this narrow, but if you have many, many of those locations, it smears it out, of course, and you see a very broad line, if I call this a line, this zero order maximum. We have here a grating that works not in transmission. Your grating works in transmission. The light goes through it, like what we discussed here. But we have here one that is metal, whereby grooves are put on the metal. And this is called a reflection grating. And I can show you with this reflection grating, which has a large light source, just like this, it's large. I can show you the spectrum when we project it here on the screens. If Marcos can give me a hand. Thank you, Marcos. So we have white light that goes onto this reflection grating. There's a big spot of white light, and you will see then the first order will not be narrow because the light source itself is so big. And then you will see on either side something similar to what you saw here. You will see the white, the zero order, is always the light of the source itself, which is, in this case, white. And then on both sides, you will see first order, second order. And I think you see up to 4 or 5 orders. I don't remember how many lines there are per inch. It's not important because it's really the effect that I want to show you. I was quantitative on my own demonstration with my green laser. So let us turn this on. I think that's it. And we turn all the lights off so that you can enjoy this in its full. So here you see the size of that zero order maximum. It's not narrow at all, because the light source is not narrow. And then you see here nicely the blue, the green, and you see here the red, blue, green, red. You begin to see spectra, and then the whole thing sort of peters out, and you see the same on this side. So this is a reflection grating. If we turn on a laser, a red laser, which is much narrower, then you get the advantage of your many, many lines, and then you get, of course, an extremely narrow zero order maximum. And that is this laser, I believe. We will know very shortly. Yeah, so this is the 633 nanometer laser. And so now I take advantage of the many lines that I cover. And now my light source is narrow enough to let me benefit from the grating, the many slits that I use. And you see, as you expect, that the red zero order always falls at the same location. And then the red here, the 633, coincides, of course, with the red from the white light and so on. And you even see here 633, and I don't think so. This is first order, second, third order. There is no fourth order. The separation in terms of angle is only a function of d, the spacing between the grooves, and of course lambda. And so if the spacing of a double slit interference pattern is the same as the spacing of a multiple one, the separation in angle is the same. But of course, you get, the gain is that you make them narrower and they go up with n squared. So that's what you gain. So now I would like you to take full advantage, thanks Marcos, to take full advantage of your grating. And we have prepared light sources which are narrow enough so that you come very close, maybe not exactly, you come very close to seeing the width of the light source about lambda over nd. If you put the grating in front of your eye, your pupil itself has a diameter of about 3 millimeters. So you will only use effectively with your eye about 1600 lines, just like my laser beam did, because the same 3 millimeters. So you look through about 1600 of these lines, and you know what the d is, the separation of the grooves. And so you can now look at a line source which we have prepared. So we have prepared line sources which are very narrow, not like this one, but very narrow, which are in here. And now if you look at that light source, which is helium, and now you use your grating, then you begin to understand the idea of spectral resolution. You will now begin to see the individual atomic lines nicely separated through your grating. And so we'll turn this on, and we'll make it completely dark. And then I want you, thank you, and I want you to appreciate this and spend some time looking at these lines. It's really quite remarkable. And this, of course, you could never do with a two-slit interference. You need these many, many lines. You look through about 1600, this very strong yellow in the helium is a well-known helium line, and it has a wavelength of 587 nanometers. It's the brightest, the strongest one in helium. And you can see them in first order, you can see them in second order, and then gradually, when you go to higher orders, the various colors begin to overlap with each other because they each live their own life. The angles are only dependent on lambda over d. And now I can show you neon, which has even more lines. And so you can look at your grating. Amazing, you know, this grating doesn't cost more than maybe $1. It's absolutely stunning. And it has an incredible spectral resolution already. But because you need a prepared line source to take advantage of that spectral resolution. And as I said, you will probably approach, certainly the audience all the way in the back of 6120, they will approach this angular resolution. The ones that are closer may not approach it because they see the line source, of course, wider. The angle at which they see the line source may well be larger than this width. But the ones in the back of the audience are therefore a little better off. So the angle that you see to the line source, the width of the line source becomes smaller the farther you are away. This is remarkable, isn't it? Absolutely incredible. So I think this is a great moment to rest and to digest this wonderful experience and to have a 4-minute break. Thank you very much. So what I want to discuss now is the logical consequence of this whole concept of Huygens sources where spherical waves come from each point in the aperture. And we're now going to extend it to a single opening. Not multiples, but one single opening. And the opening is now D. So this separation is now, this opening is D. But think of them as being a slit which has a width D. It's open, single slit. And we have plane waves coming in like this. And now the question is, if I look in various directions, and that's my famous angle theta, what will I see now on a screen which I place very far away? Well, each point in this aperture can now be considered, according to the Huygens-Fresnel principle, as a source of spherical waves, and they are going to interfere with each other. Strangely enough, for reasons beyond me, we call this diffraction. But it's exactly the same phenomenon as interference. But we draw a strange distinction in physics between interference, which was the grating, and the double slit. We say double slit interference. No one would ever say double slit diffraction, but it's the same thing. Somehow when we deal with individual openings, we call that diffraction. So it is the same. You can use it any way you want to. You can call it interference. But the individual Huygens sources, there they are. They're all going to do their own thing. And I pick this one at the top, number 1. And I pick this one, number 2, right in the middle. Why don't I do that, right? You will see why I do that. So now I can calculate what the path difference is between the Huygens source right in the middle and the Huygens source right in the top. Well, this path difference here is clearly 1/2 d times the sine of theta. We did that before. We had a little d here. If I make that 1/2 lambda, I claim that in that direction there will be darkness. Why will there be darkness? Because if source number 1 can kill number 2 because they are 180 degrees out of phase, then the source just below 1 can kill this one below 2, and the one below there can kill this one, so I can always identify 2 pairs which kill each other. That means darkness. So this must be a criterion for destructive interference. Now, it may not be the only angle for which there's destructive interference, but I want to convince you that there is at least one for which you see no light. I will now introduce a phase angle beta, which is the phase difference between source 1 and source 2. So, if this is the slit, one side of the slit and the middle of the slit. It's not the phase angle between 2 neighboring sources, because the neighboring sources touch each other. There's an infinite number of Huygens sources. It's a continuous Huygens source. So it is the phase angle between the edge of the slit and the center of the slit. That's the way I define beta. And so my beta now becomes 2 pi divided by lambda times this, times 1/2 d times the sine of theta. And so you see the 1/2 eats up the 2, so you get pi d divided by lambda times the sine of theta. And now I will not derive for you, as I did so precisely for the gratings, I will not derive for you what the light intensity is a function of angle. Again, it is a matter of adding vectors. But you can look that up in Becker and Barrett. It's done in section 8.7. And so I will only give you the answer. I did it for the grating. You do this one. And you can show now that the intensity of the light as a function of that phase angle beta is I0 times the sine of beta divided by beta, and of course no surprise that you get a square there, because that has to do with the pointing vector. And this function is very different from a grating function. And before I plot it, let me make a few calculations. I'll do it here on the center board so that you can still compare with this equation. So I'm going to write down here what the sine of theta is. And then here in my column comes beta. And then here comes the sine of beta. And here comes the intensity I. So I first take the sine of theta is 0. Well, if the sine of theta is 0, it's immediately obvious that beta is 0. And it's also obvious that the sine of beta is 0. So you get 0 divided by 0, you use L'Hopital, and this ratio becomes 1. And now the light intensity is I0. Well, that's not so surprised that you have there a lot of light, because, of course, if you have an opening here, and you shine light through it, then you expect that you see right on the wall there, in the middle of the slit, you expect to see a lot of light. So that's not so surprising. This, by the way, is the way that we define I0. So I0 is defined as that maximum that you will see when you, so to speak, look straight forward at an angle theta 0. That's the way we define I0. So now let's take sine theta is lambda divided by d. So now beta is pi. I mean, put in here, sine theta is lambda divided by d. Here it is. So you see that beta is pi. So the sine of beta is now 0, and therefore the intensity is 0. Because the upstairs is 0, but the downstairs is not 0. Ah, that's this. Because look, if you take this half away and you take this half away, you get that the sine of theta is lambda divided by d. I already predicted that you would have destructive interference. That's exactly this case, of course. And now I have 2 lambda divided by d. So that gives me a beta now of 2 pi. That gives me again a 0 here, and there's another 0. So there are more locations in space where there is complete darkness, not just one. In fact, there's an infinite number of them. You can go on like this. I will first plot the curve, and then we will discuss it in a little bit more detail. And I will only plot curves in terms of sine theta, because that is an angle that I can relate to. I can tell my mother about theta. I can't tell my mother about phase angles, but I can tell her about theta. Mom, this is theta, 10 degrees, 20 degrees, 30 degrees. That's a real angle in my laboratory. That is that theta. So that I can relate to. I always plot things in terms of sine theta. And so here is my 0. And let this be lambda divided by that capital D. That is the slit width. This is 2 lambda divided by d. And here is 3 lambda divided by d. And on the other side, minus lambda divided by d, and so on. I'll put one more in. And so now, the curve that you see, not so obvious, but when you plot it, you will see that. You get here this maximum, which we define to be I0, is the central maximum. And then you'll get here your first 0. You get here some kind of a mini maximum. And then you get another 0 here. And you get an infinite number of zeros every time. You get 3 lambda over d, 4 lambda over d, 5 lambda over d. And on this side here. And so on. So the central maximum, the width in terms of angles, think of this as angles, right? Sine theta is close to theta in terms of radians. So this is an angular size. The linear size depends on how far you are away from the screen on which you show it. Then you have to multiply this by L, if L is the distance to the screen. This is the angular size. So this width here, very crudely, is about half this. And so that width is about lambda divided by d. So let's take an example, which is, I think, the demonstration that I have lined up for you anyhow. We'll take laser light, which is about 600 nanometers. The fact that it is 633, of course, is not so important. I give you easy numbers. And suppose we have D, which is about 0.1 millimeters. So we have a slit, which has a width opening of only 0.1 millimeters. And we'll put a screen there, L, at a distance of about 3 meters. So we can calculate now what lambda divided by d is. So that would give you the angle in radians. That is 6 times 10 to the minus 3 radians. Sine theta is very close to theta. And so now you can calculate the linear size of this central maximum, as I'm going to show you there on the screen. And that linear size is now L. So the linear size, the linear dimension, is L times lambda over d. So that's how wide that central maximum will be. And that in this case will then be about 2 centimeters. Now think about it. Think about the absurdity. We have a slit which has an opening of 1/10 of a millimeter. And because of Mr. Huygens, it will show up there with a width of 2 centimeters. 200 times broader than the actual opening. Whereas, if you would think high school, then you would say, well, if you have light going through a 1/10 of a millimeter, and you look what you see on the wall, you see a 1/10 of a millimeter. No, you see 2 centimeters. And that's the result of diffraction. That's the result of the fact that each one of those sources in this aperture are going to radiate spherical waves. They are going to interfere with each other, and they then cause this huge broad center. And the smaller you make D, the more you tighten the nuts on the slit, the wider it's going to be. Because look, if you make this smaller D, then this angle will become larger. very non-intuitive. Before I show you this, I want to know roughly what that maximum is here, that mini-maximum. Well, that's easy. You could do that now on your own, because all you have to do is you have to substitute in this equation sine theta, which is sort of halfway in between. So if I do that, halfway in between, that is 1.5 times lambda divided by d, right? That's right in between these two. So that gives me then a beta of 1.5 pi, 1.5 pi. I can go to this equation, and I put in for sine theta 1.5 lambda over d. So the lambda and the d cancel, you get 1.5 pi. Straightforward, just turning the crank. So now you have beta, and you can calculate what the sine of beta is, which is -1. And so now you know what the sine of beta divided by beta is, and you'll find 0.045 times I0. So this mini-maximum is 4.5% of the central maximum. And when you go further out, these maxima are even smaller. But when I show you this phenomenon, which I will, you will see distinctly these zeros. You will see actually very nice dark locations, and you'll see the central maximum and then a little bit of light, but not very much light on this side. And of course, again, this is wavelength dependent. So whether you do this in red light or in blue light, you will see something very different. If you do it in red light, you will see this wide. If you do it in blue light, you will see it narrower. And also those locations, of course, are then further in. And I have a slide which shows you the idea in different colors. Maybe we can make it a little darker if you use the TV button. Thank you, Marcos. So here you see it in 3 colors, red, green, and blue. So notice how very different this is from a grating. You see some broad central maximum. That is that central maximum that you see here on the blackboard. And then you see the sharp black locations where there is almost no light here. And you see them for red farther apart than for green, and for green farther apart than for blue. And then when you do it with white light, of course, then it becomes always more difficult to see the sharp dark areas because the colors overlap. All right, so now I want to demonstrate this to you. And the way that we're going to do this is with a slit that we can vary in size. So I'm going to do this with 600 and, where was my calculation? I made a calculation here. So I'm going to do it with a 633 nanometer laser light. And the slit, so the beam of that laser is about 3 millimeters, and then we have a slit here. So this is the opening, so this is the D, and we can make the D smaller. And so we already made a prediction that the linear dimension then, if the opening is only 1/10 of a millimeter, you would expect that the central maximum on that screen, which is about 3 meters away, that's why I chose the 3 meters, that central maximum will then be 2 centimeters wide. But I can make it way wider, because I can make D way smaller than 1/10 of a millimeter. This is it. There you are. All right, so what you see now is that the slit is very large, very open. I don't know, maybe a millimeter or so. And I'm going to tighten it. And I'll stop at one point here so that you can, this is a nice moment to stop. So here you see that central maximum. See how powerful and overwhelming that is in terms of its brightness. We understand now why, because of this crazy function sine beta divided by beta squared. Already now, it is here, I would say 5 centimeters. So already now, the slit width must be less than a tenth of a millimeter, because it would be 2 centimeters if it were a tenth of a millimeter. And I hope you can see distinctly those dark locations. And you see there are a lot of them. But keep in mind that this mini maxima next to the broad maximum is only 4.5%, and it gets smaller and smaller, lower and lower as you go further away. And so now I go way beyond 1/10 of a millimeter, way smaller, way smaller. Now keep in mind, when I make the slit width smaller, less light will go through. I can't help that. So the whole image will become fainter. That's the price I pay for letting less light through. But what I gain is to show you the absurdity that the center maximum gets wider and wider and wider as I make the slit smaller and smaller and smaller. So the slit is now narrower and narrower and narrower and narrower, and the central maximum that you see there is almost a foot. So the center, the opening of my slit must now be something like maybe only 10 microns or so. Extremely, so this is a very highly accurate device whereby we have the option of making the slit width indeed as small as 10 microns. And you see this is the result that you get. So I will now make the slit open and open and open and open and open. And here we have the point. If I make the center point about 2 centimeters, then the slit width, which is about now, is about 1/10 of a millimeter. All right. I now have to make an important confession about the grating equation. Some of you who were very observant may have noticed that the maxima of the grating that I showed, also when I did the experiment with my own laser, they were not all exactly the same brightness. There was a difference, and no one asked me about it, and I was hoping that no one would ask me. And the reason for that is that each one of those grooves has a finite size opening. And each one of those openings act this way. They cause diffraction. We call that diffraction, right? That's just semantics. And so superimposed on the grating equation, this causes diffraction, and the net result then is that you get the product of the two. So if I amend here now, and now I'm removing this beta now, because this is now for a grating, but the beta is defined this way. This D is the opening of each groove in your grating, and little d is the separation between the grating. Then I can write down now here times the sine of n delta over 2 divided by the sine of delta over 2. And now I put here the square. And now I have the real grating equation. And so what you see now is that since little d is always larger than capital D, you're going to see that the maxima, which come from this equation, are being modulated by this one. And so if this were a grating, whereby capital D was the opening of each individual groove, and if the grating wanted, of course, the zero order maximum will always here, and if the first order maximum of the grating would fall here, and the second order would fall here, and the third here, then this is the price you pay for the fact that these grooves have an opening. And so you see a modulation in the strength of your first, second, third, fourth order, and so on. And so when you look carefully at the grating lights, and I will demonstrate that to you, they are not all 16 times I0 if you had n equals 4. And if you have n equals 1,000, they are not all 1,000,000 times I0. But they have this overall envelope which modulates it, and that's the result of the opening, the finite opening of the grooves. So to make sure that you understand the difference between D and the two Ds, so if this is my grating, and this is the open area, so this is, say, where the light cannot go through, then the definition of D is this, and the definition of this is D. And that D shows up in here, and this capital D shows up in there. So this is the single slit diffraction, and this is the multiple slit interference. There you see again, we make the distinction in wording, but that has no meaning because it's all diffraction, of course. If somehow D were approximately D divided by 5, and it just so happens we have a grating here for which that is the case, then the 5th order maximum of the grating is going to be killed. Because that is when this function becomes 0. So you would see then 0 order 1, 2, 3, 4, 5 would be killed here, and then they would build up a little again, and then ultimately, of course, they would all peter out. And so if I show you a spectrum of a grating, you can actually roughly estimate what the ratio capital D over little d is by seeing by sort of that modulation pattern. And so that's what I want you to see now. It's not so exciting. Many of you who were observant may have seen it anyhow, because it was every time there, even when I showed my own grating. So we're going to make it quite dark for this. Oh no, this is the wrong switch. There are so many switches here. There we go. So this is a grating that I purposely offset. I purposely offset it so that here is the 0 order. Make sure, yeah, this is the 0 order. I think it's that one, actually. It's easy to test where my 0 order is. Okay, this is the 0 order. So we aim exactly here. And so this is the 1st order, 2nd order, 3rd order, 4th order. Look at this sucker. It's almost gone. That is the result of the fact, the single slit interference. And then it comes up again here. And the reason why it comes up again, because now you enter this little mini maximum in the single slit interference. So you see it here quite well. Sometimes with gratings you can see it remarkably well. Other times it is harder to see. It depends, of course, on how many maxima you have. But here you see quite well the modulation. Right? You see it comes up here again, and here this little point here would then be somewhere here in this maximum. So this is then the complete equation that combines single slit diffraction with multiple slit interference. If we change a single opening from a slit to a circle, your eye is a circle, your pupil is a circle, then very little changes, except, of course, if you have a circular opening, everything is now axial symmetric, and so you get circles. These things become circles. And then, which is not so obvious, that is that this minimum doesn't fall at lambda over 2 in terms of angular dimension, but 1.2, 2 times lambda over 2. And if you want to use 1, 2 for an approximation, that is fine enough. So it's a little larger for an opening, circular opening, than it is for a slit. I have here one of those pinholes. So this is now a circular opening for which this relation has to be used now. So this central is then a little wider. And we are about 4 meters away from the screen. It's this one, 4 meters away from the screen. And I'm going to do this with a wavelength lambda of 594 nanometers. So it is a circular opening, call it a pinhole, and lambda is about 594 nanometers. It's also a laser. And the distance to the screen L is about 4 meters. And what you're going to see is a ring, which is this ring, and then you see this light inside, which is very difficult for me. This is the very high maximum, and then you will see more rings outside. This ring is quite well defined. You're going to see that very sharply defined. And if this ring, which I measured, is about 5 centimeters in diameter, you should be able to tell me what the diameter of the opening is. of course, because you know now what the angle is, and so you can calculate what d is. And when I did that, I came up with something like, I think, 1/8 of a millimeter or so, but you can confirm that. So a very small opening of 1/8 of a millimeter, if I did that correctly, would then give you a central maximum, which is from 0 to 0, 5 centimeters wide. So let's take a look at that. These single pinhole diffractions are always very difficult because the pinholes have to be so small to see it, and that means very little light will go through. And so here you see it. For those of you who were sitting close, you clearly see that central circular maximum. And then you clearly see the first ring, the dark ring. My pinky is right on it. This is about 5 centimeters across. I see a second dark ring, but if you're far away in the audience, you may not see that so well. But this is a nice example of circular single-slit diffraction. To make you see it even better, we have handed out cards. And those cards have a small pinhole, one location, and they have double slits in the other location. And so I'm going to aim at you very slowly. I'm going to scan this over the audience, a light-emitting diode, bright light. And as it passes you, you only get one shot at it, and you look through it. Maybe we can make it a little darker. If you look through the pinhole, you will really see beautifully this circular, this ring structure with the dark lines and the center maximum. But if you look through the other opening, you will see the beautiful double-slit interference. And notice that the width of the dark lines and the width of the bright lines is about equal, because you only have 2 slits. Remember, you get this cosine square function. So it's not as dramatic as a grating. And now I'm going to rotate this through the class so that each one of you get a chance to look through both openings, one at a time. If I go too slowly, let me know. And you can keep this card, but you need a very bright light, and you need a very small light too, because the light is too large in size. Then, of course, your dark and your bright areas are going to merge with each other, so you wash it out. So your light source always has to be carefully thought through in terms of its dimension, in terms of the angular dimension. If the angular dimension of your light source is too large, you kill all the phenomena. I'm going to rotate it back. Who has not seen it? Who has not seen it? You have not seen it. Amanda, how could I do that to you? But now you can see it even longer than others. This single-slit diffraction, or single-opening diffraction, has major consequences even for our daily experiences, because it ultimately determines our ability to separate 2 light sources in the sky. If you have a telescope, and the telescope has a lens, or it has a mirror which has a diameter d, then there is a limitation to which it can separate 2 stars in the sky. Let's assume there are 2 stars at roughly equal strength. So here is star number 1, and here is another star, which is star number 2, and the angle between them is delta theta. Then somewhere here on a photographic plate, or in your case on your retina, there will be an image, and that image will be like this for one star, and there will be another image a little bit displaced from the other star. And if those 2 blurs are too close together, you don't see 2 stars anymore, but you see only 1 star. And so now comes the question, how close, how small can this angle be so that you still say, yeah, there are 2 light sources. A car comes to you with 2 headlights. How close does the car have to be that you still say, yeah, there are 2 and not 1? Well, that is a criterion which is a little bit arbitrary. It's called the Rayleigh criterion for angular resolution. And that is, we want the angle between the 2 lights larger or equal to this angle, so that the maximum of the second light would fall here. And so you would clearly see then that this thing is broadened, and you may even see a little dip in that curve. So on your photographic plate, you would really be able to say, yeah, there are two sources, and there is not just one source. And so the angular resolution would then be, in terms of angle, 1.2 times lambda divided by d. So delta theta would have to be larger than 1.2 times lambda over d for you to be able to say, yes, there are two stars, which is the ultimate limit of angular resolution for you, for me, but also for optical telescopes. Suppose we take the Hubble Space Telescope. Hubble Space Telescope, HST, has a mirror D, which has a diameter of 2.4 meters. And it is prepared so carefully that the claim is made that it is really diffraction limited. And so that means if I take an average wavelength, the optical spectrum of about 500 nanometers, I realize that all the way it goes from 400 to 650, but if I take this as a representative wavelength, then 1.2 times lambda divided by d translates into about 1/20th of an arc second. That is an incredible resolution. 1/20th of an arc second. If two stars equal brightness are 1/20th of an arc second apart, Hubble Space Telescope can see it as two stars. The same telescope on Earth would do no better than half an arc second, this is an arc second, to maybe even 2 arc seconds. Why is it so much worse for a telescope on the ground than it is for Hubble Space Telescope? Any one of you know that? Atmosphere. The Earth's atmosphere is in turbulence, is always in motion, thermal motion. And it is that thermal motion that is the problem. That makes your image on your photographic plate or on your CCD move around. They work like little lenses, and so it broadens it. But it broadens it in an incredible way. If you're seeing, we call this the seeing. If the seeing were 1 arc second, then Hubble's telescope, which is above the Earth's atmosphere, has an angular resolution which is 20 times better linearly. That means over a surface, it has 400 times more resolution elements because it's two-dimensional. So it's highly superior in terms of angular resolution than any ground-based observatory. And now comes your human eye. Your human eye. The opening of your human eye depends on the time of the day. At night, when it's dark, your pupil opens. During the day, it goes down a little. If we take about 4 millimeters, a reasonable number, and we take again 500 nanometers as our representative wavelength, then we can calculate what 1.2 times lambda over d is, and that translates to half an arc minute. That is 30 arc seconds. That is 600 times worse than Hubble Space Telescope. You cannot do better than this. This is Mother Nature. You cannot beat diffraction. On your retina, when you look at a light source, the image on your retina will look like this. Will look exactly what you saw there. That is what your retina will see. And if those two lights are too close together, your brains will say, sorry, I don't see two lights. Now, in practice, Mother Nature did not design our eyes, at least most of us, not really down to diffraction limitation. In practice, I think it's more like 1 to 2 arc minutes. This is my symbol for arc minutes. So the angular resolution of your eyes is not quite as good as it could be, but it is close to that. And I'm going to test that with you. I have here a screen. And this screen has holes in it. And I'll give you the code of the holes. So here is that screen. 2 holes, 2 holes, 2 holes, 2 holes, and we repeat them 3 times. This is 1 millimeter apart, 2 millimeter apart, 3 millimeter apart, 4 millimeters apart. Students who are 2 meters away, very few are, but if you were 2 meters away, so we take here a student who is at a distance of 2 meters. If the student looks at the 1 millimeter separation of these slides, then the angular separation is 1.7 arc minutes. So you should be able to see them as two lights. If you look at the 2 millimeter separation, then obviously it's about 3.4 arc minutes. You should have no problems. In other words, the students who are close should be able to see this as two lights, this as two lights, and this as two lights. But let's now go to the students who are 5 meters away. So this is the students who are 5 meters away in the audience. If we go to the 1 millimeter separation, there is no hope on earth that you will see that when you're sitting there where Christine is sitting. You will not be able to see the upper two as two light sources because the separation is only 0.7 arc minutes. And I don't think that any one of you can see lights that are 0.7 arc minutes apart. The 2 millimeter slots would be 1.4 arc minutes, and the 3 millimeter slots would be about 2 arc minutes. And so I'm going to make it dark now in the room, and I want each of you just look at these pinholes, and I'm going to rotate this so that all of you get a chance. And then I want you to raise your hand if you can see the top two as separate ones. And only those who will raise their hands will be very close to me. And then we will slowly go farther into the audience. So look closely at the upper one. And then also try to see the one below there, which are the 2 millimeters, which are here, the 3 millimeters and the 4 millimeters. Can you see the upper one, Amanda, as 2? Even the upper one you can. You see you're only 3 meters away. Okay, now I will just rotate this. So the upper one, again, is the 1 millimeter separation. You see a repeat 3 times, and then 2 millimeters, and then below that is 3 millimeters, and then it's 4 millimeters. Okay, so raise your hand if you can see the upper one as two light sources. No one. Oh boy. Well, if you really can, then your resolution is very close to 0.6 arc minutes, because the 2 meters was 0.7 arc minutes. So that's really remarkable. But it's possible. Who can see the second row clearly as two distinct sources? Now people are coming in. So even the ones that are close can only do it. You see that? No one in the audience there in the back is raising his hand. So now we're talking about a resolution of the 2 millimeters, that 3.4 arc minutes for the ones that are 2 meters. So you're talking about 2.5 arc minutes. Who can see the third row separate? And now the hands go up. And who can see the fourth row as separate? I think the whole class. The ones in the back there, can you not see? Really? Boy, you got to go to an eye doctor. Really, you cannot see the bottom. I was there this morning where you were. I could see the bottom one distinctly as two light sources. And I could kid myself that I even saw this one as two, but I was really kidding myself because I knew it, I think. But this one I could clearly see. So really, none of you can see the bottom one as two different. Well, that shows that your angular resolution is no better, and you shouldn't be ashamed of that, it's not your fault, than about 2 arc minutes. So with that idea in mind, have a good weekend.